Welcome friends, Igor is here, and in this video we will define the determinant of a matrix and compute determinants of some matrices. In this lesson we will define the determinant of a square matrix, discover the cofactor expansion formulas for the determinant along any row or column, and compute determinants of several matrices using cofactor expansions. Let's get started. We are going to do something interesting in this video. We are going to take a square matrix and we are going to assign one single number to this square matrix. This number is going to be called the determinant of a matrix, and as we will discover in the near future, knowing this one single number already tells us quite a lot of information about the original matrix. There are several different ways to define the determinant of a square matrix. I will take the approach of a recursive formula. The determinant of a matrix is going to be defined recursively in terms of determinants of matrices of the smaller size. To create this definition, we need the notion of a submatrix of a matrix. Suppose that A is a matrix of size m by n. Then its submatrix Aij is a matrix of size m-1 by n-1, which is obtained by removing row I and column j from the matrix A. Let's look at an example. The matrix A is a 3 by 4 matrix, and, for example, its submatrix 2, 3 is given as follows. To obtain this submatrix, we delete row 2 and column 3 from the original matrix, and the remaining part is now a 2 by 3 matrix. Here is another submatrix of the matrix A, which is obtained by deleting row 3 and column 1 of the original matrix. The resulting submatrix is a matrix of size 2 by 3. And now we are ready to define the determinant of a square matrix. It is defined recursively in terms of the size of the matrix, and step 1 is to define the determinant of matrices of size 1 by 1. A matrix of size 1 by 1 contains just one single entry, and we defined the determinant of this matrix as that only entry. In the general case, if A is a matrix of size n, where n is at least 2, then we define the determinant of this matrix using the following formula. We take all entries in the first row of the matrix one entry at a time. We multiply each entry by the determinant of the submatrix that is obtained from the matrix A by deleting the row and the column in which the entry appears. And then we create an alternating sum of these products. This can be represented compactly using the sigma notation. Notice one important pattern. The power on -1 is equal to the row number plus the column number of the entry we're taking. This formula for the determinant of the matrix is called the cofactor expansion of the determinant along row 1. There is a simple formula for the determinant of 2 by 2 matrices. Let's say A is a matrix of size 2, its entries are A, B, C, and D, then the determinant of A is given by the formula AD minus BC. This is just a direct application of the cofactor expansion formula. The first entry in row 1 is A. When we delete row 1 and column 1 in which this entry appears, then the submatrix that remains contains only entry D. The second entry in row 1 is B. When we delete row 1, column 2, this is where this entry is located, the submatrix that remains contains only the entry C. Then we take an alternating sum of the products, and it only remains to recall that the determinant of a matrix which contains one single entry is equal to the entry itself. Next, let's compute the determinant of a 3 by 3 matrix. Please pay careful attention to the difference in notation. When a square array of numbers represents a matrix, we use square brackets to delimit this array. However, when this square array is delimited by vertical bars, this indicates the determinant of this matrix, which as an object is just one single number. Back to the computation. We will use the definition of the determinant to compute this 3 by 3 determinant. We will take one entry of row 1 at a time, and we will construct the product of this entry with the determinant of the corresponding submatrix. We start with the first entry in row 1, this is entry 3, and we look at the corresponding submatrix. This gives us the first term in the cofactor expansion formula. Next, we look at the second entry in row 1, which is equal to 2. We delete mentally the row and column of this matrix, and we construct the corresponding 2 by 2 submatrix. We multiply the entry by the determinant of the submatrix, and we remember that the cofactor expansion involves an alternating sum. Therefore, the second term gets subtracted rather than added to the sum. Next, we look at the third entry in row 1, this is -1, and we construct the corresponding submatrix. We multiply the entry by the determinant of the corresponding submatrix, and now the third term gets added to the alternating sum. As you see, this is the essence of this recursive formula. To compute the determinant of a 3 by 3 matrix, we reduced this problem to 3 determinants of 2 by 2 matrices. But we already know how to compute the determinant of any 2 by 2 matrix. The first determinant is equal to 1 times 2 minus 6 times -1. The second determinant is equal to 4 times 2 minus 6 times -3. And the third determinant is equal to 4 times -1 minus 1 times -3. Now we just do this arithmetic computation, and we see that the determinant of this matrix is equal to -27. Now you can imagine that the larger the size of the matrix, the more difficult it is to compute the determinant. Even though we defined the determinant using cofactor expansion along row 1, in fact, we can use a cofactor expansion along any row of the matrix. The pattern is similar to the definition. We take entries from one row of a matrix, and we multiply each entry by the determinant of the submatrix, which is obtained by removing the row and the column in which this entry is located. We take these products, and then we take an alternating sum. Here is a pattern for the signs of the alternating sum. It does not necessarily start with the plus sign. The sign of each term is determined as follows. You add the row number and the column number of the entry. If the sum is even, then we have a plus sign, and if the sum is odd, then we have the minus sign. You should recognize that this is the same formula as the one given in definition with 1 replaced by I. Next, let's establish that taking the transpose does not change the determinant of the matrix. This is a somewhat tricky proof, and we start by representing the determinant of A transpose as the sum of n copies of the determinant of A transpose divided by n. In this case, n is the size of the matrix. In the sum of n copies of the determinant of A transpose, we will apply the cofactor expansion along row I to the term number I in this sum. So in this double summation, the index I ranges over the rows of the matrix, and the index j ranges over the columns of the matrix A transpose. The entry in position ij of the matrix A transpose is the entry in position ji of the original matrix A, and the submatrix that can be obtained by removing row I and column j of the matrix A transposed is the transpose of the submatrix of A obtained by removing row j and column I. If you can't visualize this mentally, then please consider an explicit example of a 3 by 4 matrix to make sure that this indeed works this way. And now comes an advanced proof technique called mathematical induction. We defined the determinant of matrices of size n in terms of determinants of matrices of a smaller size, n-1. And this whole proof is based on induction on the size of the matrix A. Here is the essence of this method. We can assume that what we want to prove is true for matrices of size n-1. Namely, we are assuming that if you take the transpose of a matrix of size n-1, then the determinant does not change. This is the assumption we are now using in this step of the computation. If you don't know the method of mathematical induction, then don't worry, just take this step in the proof for granted. Next, we are going to switch the order in the double summation. The inner sum will now go along the index I, and the outer sum will go along the index j. You should now recognize the inner sum as the cofactor expansion along row j for the matrix A. Therefore, each of the inner sums represents the determinant of the matrix A. And now we see that we add n copies of the determinant of A, then divided by n, this is just determinant of A. And we have proved that determinant of A transpose is equal to the determinant of A. Using this fact, we can now establish the cofactor expansion along columns for the determinant. Notice that in this sum, the index j, the column number stays fixed, and it is the index I, the row number, that is varied. To establish this new formula, let's use the fact we just proved that the determinant of the matrix is equal to the determinant of its transpose. Then we are going to apply the cofactor expansion along row j for the matrix A transpose. But then the entry in position ji of A transpose is the entry in position ij of the matrix A, and the submatrix of A transpose obtained by removing row j and column I is the same as the submatrix of A obtained by removing row I and column j. But this is exactly the formula we were trying to establish. And now we can be a little bit more flexible in computing the determinants of matrices. We don't have to use the definition which requires expansion along the first row. We can use expansion along any row or any column. How can this be useful? Let me illustrate. Let's try to compute the determinant of this 4x4 matrix. Do you see the best approach to this computation? Notice that column 3 contains 2 zeros. Therefore, in the cofactor expansion, something will get multiplied by zeros, and therefore we will not have to compute the determinants of the corresponding 3x3 matrices. So let's apply the cofactor expansion along column 3 of this matrix. We do not need to compute the determinants of the first two 3x3 matrices because they will get multiplied by zeros in this expansion. Effectively, we reduced our computation time in half because we need to compute only two 3x3 determinants. We already worked out an example of a 3x3 determinant, so please use this as an exercise to make sure that you can compute these 3x3 determinants and get the numbers shown here. If you found this video useful, please give it a like to help others discover this content and subscribe to this channel to see more of these videos. In the next video in this series, we will discover a more efficient approach to computing determinants which uses elementary row operations. I will see you later.